I like we assume all of us are aware of the GPU and all these things, like why we need GPU and things like this. But it's always good to discuss things that we know and make ourselves, revise on some of the topics. So let's start the presentation. The main objective of this initial part is to get some overview of historical development of microprocessor, how it evolved, and also to understand why we are using GPU and how it could scale the computational power. So we already have a CPU, but we want to know more about GPU and how it could excel the computational power. Moving forward, so when we talk about history, so this is the first thing that we have to keep in mind is Moore's law. So Moore's law is something that was like observation or forecast made by Gordon E. Moore. So he is the co-founder of the Intel, and what he states is that the number of transistors that can be placed on an integrated circuit, it doubles approximately every 2 years. So since this forecast was made in 1965, so the assumption was like every 2 years the transistors would be doubled, and every time we double the transistor, the transistor density becomes double. That means the computer it becomes faster, right? So for instance, Apple's 8AX processor in 2014 it has around 3 billion transistors, and it was powerful supercomputer is that in back in 1995. So it took us around 20 years of this chip development process where we could wrap a powerful, highly specialized scientific supercomputer into a consumer device. So the iPad and all these things that we're using today is all because of these things. Moving forward, same with the Moore's law. So if you see here, in 1970, we have around 1,000 transistor placed here. But when we reach in 2010, so it is around 1 billion that is the transistor placed in a single chip. So you could easily imagine how this could scale up the computational power and all those things. Now we talk about transistor, but why transistor inside the computer? So the reason behind our computer being so powerful is that computers are built with number of chips that we call integrated circuits, and these integrated circuits are built with a lot of transistors, and they are like small conducting lines that helps the electric current to flow through it, and we use this electric current as a switch. So either it could be on or off, and this on and off state help us to encode the information and do some calculation or some computation. So we can use this transistor or to manipulate them either to let electric current flow through the specific conducting line or not. And these are really helpful inside the computer. So for instance, if you want to do any basic computation or operation inside your computer, so when we add two numbers, it is 8. Like for instance, if we add 5 and 3, it is 8. And it is represented by number 1,000 inside the computer. But the way it works inside is like you see here. So these numbers are converted into bits. And now when there is an electric current that is passing through it, then it is represented as 1. And if there is no electric current, then it is represented as 0. So based on this, you'd get the number. And inside the computer, this number is represented by the number that human understand. So basically, like we use all this transistor and all these chips inside to turn human readable information into machine readable information, and back you get like a human readable information. So this is how the computer works. And the more chips, the more transistor we have, these operations are done in a faster way. So moving forward, we understand about the transistors, and now if we want to do some computation in parallel, so what does this mean? So parallel computing, it involves dividing some like a computational problem into a smaller and independent subtasks. So our goal is to do some computation in parallel. That means like we have to divide our tasks into smaller chunks so that we can process them simultaneously, and we have different multiple processing units inside our computer. Then it will be used to process, and the overall computational time is slow. So, for instance, you could imagine like in a kitchen, if like some of the chefs, they are working together, and then they give you some fast foods in a fast food restaurant like burger. So they all will be doing some small part, and then you just have to wait few minutes, and your dish is ready. So this is also like we can think of the working mechanism in this way if we want to relate. Like when we talk about computing parallel, I just want every one of us to think behind our head, like, is there any other real world problems that could be solved using parallel processing or computing? Like you could just think back of your head, and you could also write in the the documentation. It would be extremely beneficial to discuss. And when we talk about parallel processing, so there are some challenges as well. So let's discuss some challenges. And I want, if you have something in your head that could show some challenges, then we want to discuss that later in the from the documentation also. So moving forward, when we say we can do parallel processing, yes, of course we can do, but there are some challenges, and we have to be aware of these challenges. So the first thing is that the data dependency. So when different tasks are done by different processors, then there's like one of the processors may wait for other tasks to be finished. Then the result is like a bottleneck. You get the result from one processor, and then next processor would continue. So it's like a data dependency sort of thing. And sometimes there is like uneven load balancing. So there are like multiple processes, but you delegate lot of work to one process, then there's few tasks for other processes, then it's like uneven load balancing. So we also have to take account into this thing. And the second thing is like the communication overhead. So you want your processors to effectively perform some operations for you, but if there is a lot of time that needs the processor to communicate or transfer the data, then it's like also a problem. And the other thing is that, okay, we have multiple processing units, and then every one of them are working. It is fast, but what if there is like a synchronization issue? What if they don't synchronize well? So this is another thing. And the scalability. So I guess this is one of the quite interesting part. So we say, okay, we have a lot of processors, but are we clever enough to define our problem? Is it scalable or not with more processor? Sometimes we easily say that, okay, I have a problem. I have a lot of processors, and then it will do my job. But we also have to see whether our problem is actually scalable or not, whether our problem fits into this multi-processing thing or not. So these are some challenges when you try to think of parallel processing. Moving forward, so now we want to discuss a bit about GPU. So what is GPU? So we already have CPU inside our computer, and why the thing GPU exists or so. So GPU, they are like specialized accelerators. And we all know that initially they were developed for like graphics processing tasks. So everything that is rendered on your screen with a lot of cool colors and all these things, it's because of GPU. So, but over time they have become essential in high performance computing as well. So initially, even if GPU were developed for like graphics rendering purpose, so these days when we need to do a lot of computation, like high performance computing, so GPU actually become quite useful for that. So GPU are like specialized parallelized hardware for floating point calculations, and they are basically co-processors, like helpers for traditional CPU. And CPU still controls the workflow, but it delegates highly parallel tasks to the GPU. So GPU are basically helping CPU to do the highly parallelized tasks, so that in combination they give you like a better performance. And GPUs are based on highly parallel architectures, which allow you to take advantage of the increasing number of transistors. So we discuss about transistors, and it is GPU that helps you to use these transistors in a way that gives you some advantage. And when we talk about high performance computing these days, you see like there are a lot of domains like for fast Fourier transform, matrix multiplication operations that could be highly optimized for execution on GPU. So these tasks, it leverages the parallel processing capabilities of GPU, and it helps you to give the significant improvements over the traditional CPU based computation. So when we talk about matrix multiplication, you would always see like different nested loops where you have like nested loops 1 or 2 or 3 level, and there is a small computation inside that nested loop. So if you see like every time you go inside that loop and the computational part is the same. So if you try to use GPU for this sort of tasks, then the performance is quite good. Moving forward, let's discuss a bit about the architecture of CPU and GPU. So here you see on CPU you have like core 1, core 2, like core 4, but in GPU you have multiprocessors, and then each multiprocessor has a number of cores inside it. And when we talk about architecture, one thing we have to keep in mind is like we have to know like some of the thing about host and device thing. So GPU enabled systems, they are they require a heterogeneous programming model which involves both CPU and GPU. So CPU and its memory is referred to as the host, and the GPU its and the GPU is referred to the device. Moving forward, when we talk about this heterogeneous model, we can try to think a use case for like CPU GPU interaction. So, for instance, when a developer writes code for a CPU, so it could also include tasks for GPU like rendering graphics or do some complex calculation that would be time consuming. And what CPU does is like it sends the command to the GPU via the GPU driver, and it is responsible for managing the communication and task execution. And the GPU, it processes those commands and do the operations as needed. And when when the calculations or when the operations are performed, the GPU sends the output in form of image or some 3D models, something like this, back to your CPU through the GPU driver again. And it is CPU that uses this output to update the screen or continue the processing. So essentially, it is like the GPU is doing the computational in a way that it makes it fast, and then it helps the CPU. Moving forward, so when we talk about this host and device again, if you are doing some CUDA program, you see a lot of instances where you write some code like this: CUDA memcopy host to device, like where device is again we said like as a GPU and host is CPU. So these all things are like inside the CUDA program where you do the memory copying from host to device. And the job of the host is just to prepare the data and manage the workflow, like CPU tasks as shown here. And the GPU, like the device, it executes the parallel tasks and do the processing simultaneously across different multiple threads, and then you would get a significant time reduction on your problem. If you look at this slide, what you see here is like this is a top 500 list. So this is the snapshot that shows like top 5 HPC systems as of June 2023, I guess. Yeah, and you see like these sections. It shows core and number of number of processors and maximal link pack performance achieved are peaked power consumptions, and you see like the one that would be using Lumi, so it's in top 5 in the world, so we'll be doing our exercise session in Lumi. So So yeah, so with this background information, now we are curious, like, why do we need GPU? So as we already discussed, like, uh, we want to do our tasks faster. So speed is one of the main reason why we want to use GPU. So GPU computing, it can significantly accelerate many types of scientific workloads. So these days we have huge workload in terms of scientific domain, and we want to use the capabilities of GPU for this one. And also, another thing is like energy efficiency. So compared to CPUs, like GPU can perform more calculation per watt of power consumed. So this result in significant energy saving. So if we talk about energy efficiency, so GPU is also is quite worth it. And other thing is like cost effectiveness. So GPU, it could be more cost effective than a traditional CPU based system for some certain types of workload. And we again say that we need to understand our workload, and if we understand, okay, this is something that GPU can handle well, then it is cost effective as well. Uh, we we discussed like, okay, GPU, like they really have some importance, but also there are some limitations when you try to use GPU. So for instance, GPU are suitable for only certain workloads. Not all workloads can be efficiently parallelized and accelerated on GPU. Like certain types of workload, such as like irregular data access pattern or high branching behavior, it may not see significant improvements on GPU. So when we talk about efficient workload, some image processing tasks like applying filters where each pixels can be processed independently. So these sort of works are like efficient workflows, and they are ideal for GPUs. But if we talk about this irregular data access pattern, so if we talk about some graph traversal algorithms like depth first search or breadth first search, that involves exploring each node and edges in a graph. So this sort of algorithm, it requires a lot of dynamic decision making, and the data access pattern is irregular. So this sort of workload is not good for GPU. So we really need to understand what sort of workload we want to uh, do so to use our GPU. The second thing is the learning curve. So if we want to use GPU for our computation, and then we need to learn a GPU. So GPU computing, it could require specialized skills in GPU programming and knowledge of GPU architecture. So for instance, if you want to learn CUDA, so it also involves a lot of sections where you need to understand concepts like memory management, like kernel launches and thread synchronization. So typically in a CPU program, you don't encounter these things. So you have to be really effective in all these things if you want to perform GPU computing. So the learning curve in the beginning is quite, it could be steeper, but we are here for that purpose to assist you. So the key takeaways of this initial part is like, so we have GPUs, which are accelerator for some types of tasks. We need to understand what our task is, and GPU, it is highly like parallelizable compute intensive tasks are suitable for GPUs. So if our task is like highly parallel and it requires a lot of computational power, then we have to use GPUs. And then in order to do GPU programming, we need to learn some new programming skills. So these are the key takeaways from this part. And we again say that we assume that we all are quite familiar with it, but it's just a revision for us, like why we want to use GPU and what are the things that we need to discuss. Thank you.
Thank you. So I hope by now that you are convinced that it's worth to use GPUs, and it's worth the time, the extra work to write codes for GPUs and use them efficiently. So GPUs are just fast. So because they, as was mentioned previously, they are built for parallels. So this is why when you compare them to GPUs, we see that they have very different structure. We have many transistors which are dedicated to computations, and very small amount of transistors that are dedicated to caching and to control. And the way to use them is to have lots of threads that use the GPU, that do the same, fill up the GPU and do the same operation at the same time. So now, of course, this means that we cannot just plug this in the computer and then start using the GPUs and think that things will work. So with the GPU, we also need software layers that is provided by the hardware producer. So when there are three GPUs producers at the moment. So we have NVIDIA that has been the first one to actually do GPU computing, and has been, in a way, they say that they democratized the HPC. And at the moment, they have the higher share of the HPC, of the market, of the HPC computing market. So, and then we have AMD, which is a little bit behind NVIDIA. They came into the game, they entered the game a little bit late. It's only a few years they started to produce GPUs for the HPC, but they are catching up, and now they actually doing, I think, in my opinion, they're doing quite a nice work, and you see that number 5 supercomputer in the world, it's now using AMD GPUs, and there are also other new supercomputers that are now in plan that are also going to use these GPUs from these GPUs. And then we have Intel that it seemed at some point that they're also going big and trying to get an HPC, but I'm not sure what are they doing at the moment. They are not sharing such a big market, and they seem to have lost a little bit of momentum. But still, if you look at the top 500 at the moment, Intel has this Aurora supercomputer, which is now number 2 in top 500. And they say that when it's going to be finished, then this is going to be more powerful than Frontier. So it's possible that it's going to be number 1 if nothing else comes. Nothing else comes. And so NVIDIA ships their GPUs with this so-called CUDA software suite, which contains lots of stuff that help us to program the GPUs. From AMD, we have ROCm, which is in many ways very similar to CUDA. And then we have this one API from Intel, which is also of course the same, try to help us to enable to use the Intel devices. Now, these software suites are only targeting their own GPUs. So they, in many ways, we can say that they are not going to work on other GPUs for various reasons. One of them, they don't want to support the competition, and second, also there are problems with the licensing, and also they would lose money because they will not be able to charge fees for that. But there are some cross-platform software layers, such as Direct Compute, which works only on Windows. People who have been doing gaming, they know that you need this to run you need this one to run. It's like an intermediate layer between the operating system and the game. And then we have also this OpenCL and SYCL, which give some degree of interoperability across different GPUs and accelerators. So CUDA is the NVIDIA's parallel computing platform. So CUDA contains low-level drivers and lots of APIs, which enables us to use the CPU. And also they provide highly optimized libraries for for doing matrix operations, both dense like BLAS kind of operations and sparse operation. Also, for example, you can have these fast Fourier transforms, random numbers, but also many other mathematical operations that are actually quite useful. You also comes with these compilers. So in order to program NVIDIA GPUs, we can actually use code written in all major HPC languages. We can use Fortran, C, and C++. And also what's neat about this is that we can use this developer kit from NVIDIA. So we can actually also, you can do also this kind of multi-core CPU programming using this kind of directive-based programming, which we'll see later what it's about. Now, also, I mean, when you program, we all make mistakes. So we need the CUDA toolkit also comes with these kind of tools like debuggers and compute sanitizers, so that we can actually search and for our errors and try to fix them. And in addition to this, we have tools that like NSI systems and NSI compute, which are very useful to analyze the performance of the code, find out the hotspots, and find out what parts are not efficient when running on the GPUs. From AMD, we have this ROCm platform, which was different from NVIDIA. First is that it's open source, but in many ways they try to mimic the functionality. They base their development in a way on what NVIDIA is doing good. So they use similar recipe from the point of user, looks very similar. They also support all three languages for the HPC, and they also have support for both GPUs and also multi-core CPU programming. They are not so developed in all aspects, so but they have also like equivalent debugger, LogGDB, and also they have these performance analysis tools like RockProf and RockTracers. They still have in development some tools that seem to be quite nice, and they can give lots of options. So it's called OmniTrace and OmniPerf, which would combine both the GPU and CPU. And this works up to some degree. There's one interesting feature here about AMD ROCm is that it comes with this interface portability called HIP. The idea is that when you write the code, which would work for the AMD using this HIP-C language extension, then if you have everything installed on the NVIDIA platform, then you could compile and run the same code also on NVIDIA GPU. So they are trying to give some way for the programmers to switch from NVIDIA to AMD, not to feel so locked in just one platform. And finally, we have from Intel, there's the One API. And what I like about this is that Intel, from the beginning, has been trying to promote code reusability and portability. So they build these tools and languages and in such a way that one could be able to use the same code running on the CPUs, GPUs, and also other accelerators that can be used and they give high performance. Otherwise, in many ways, they provide similar things to the ROCm and to CUDA. You have the compiler that supports C, C++, and Fortran, and also lots of tools for debugging and for performance analysis. Another interesting thing here is that in order to program GPUs, Intel here is using OpenMP and SYCL. And OpenMP and SYCL are open standards, so in a way, if you have other compilers or that support OpenMP and support SYCL and support other devices, then if you write a code that is written with OpenMP or SYCL, then for GPUs, then you would be able, in theory, to just go and run it on another device, and then we wouldn't have to do lots of work to switch between these. So there are many models of GPUs, and even in the same vendor, they support very different features. And when you write an application, it's important to be aware of what features are available, what you can use, and also it's very simple thing. When you build the binaries, you have to specify what architecture are you targeting, what model we are targeting. So if we don't do this, if we don't specify the architecture correctly, we end up with a code which actually might not run efficiently on our GPU, and also then would be possible to compile the code and then just not work because we are maybe using the wrong architecture for the binaries that is not supported by the specific GPU. So for all compilers, we have this kind of arguments that are given to the compiler when you create the code. So like basically just having these keyword architectures. We'll see the details more when you compile these for different GPUs. And then for NVIDIA GPUs, the model of that we will target is specified by this keyword SM_XY. So each generation of the NVIDIA cards has this X going from 1 to, I think now it's 9, and then you have this Y as a sub-minor version of this compute capability. And for AMD, sorry. Now, luckily, we don't have so many GPUs that are used for compute, but the ones that we have, they have this GFX, and then we have this ABC, which then specifies the architectures. So I think on Lumi this is 90A. Though there are also some other models, some other architectures from AMD that are used in HPC. So GPUs, they are not identical between the producer, but they share this design that we saw at the beginning and was also shown last previous episode. So we have lots of small computing elements, which CUDA likes to call them streaming cores. They are not the same cores as on the CPU, but we have to stick with this terminology. And these streaming cores, then they are on the chip where they have groups that are linked with that when they compute, they have to compute the same operation, and they have to do memory loads for feeding all these streaming cores. So this is called a SIMT unit. This is a term that NVIDIA invented. So it's single instruction, multiple threads. And the same concept we see that we have them on AMD and Intel GPUs, but they decide to call them differently. They have SIM-lane, equivalent of the streaming cores or streaming processor from NVIDIA, have SIMD unit, which is equivalent to SIMT unit. And from Intel, you'll hear this term, the processing elements, and then vector engine. And then we also have this kind of grouping. So one or several SIMT units are put together in this so-called streaming multiprocessor. So when threads are allocated to one specific multiprocessor, there is some degree of synchronization that can happen between these threads that are running on this multiprocessor, and also they can use some local memory that they can share data between them. So AMD decided to call this a compute unit while Intel execution unit. So in general, if you hear this term, just come back to this table and we'll see if something is confusing, we'll see how they are equivalent. And there's nothing special that they do in this regard at this level, one from another. So just message to take home from this episode. GPUs are very powerful and energy efficient, and we want to use them, but they were designed for parallelism. So because this is why they have a different architecture, they have more transistor dedicated to arithmetic operation. They can crunch massive amount of data, and basically they are applying the same operation to all of elements in an array. But this means that in order to use the hardware, you also need additional layers that come from the producer with software suites and with drivers allow us to use these GPUs, and also provide us a compiler that compiles our code that helps us to create our application around the GPUs. We also have from the producers, we get these highly optimized libraries that we don't have to write the same thing over and over. We have some problems that are very well written and optimized to work very well on these GPUs. NVIDIA has their own libraries, and AMD their own libraries, and Intel also. We also have lots of tools. Each of these software tools provides us tools to debug our code, to find our errors, and also they give us some performance analysis tools that facilitate the code optimization and maximum utilization of the GPU resources. So this was more like a summary of this self-study material from here. So I suggest to use the time, come back to this and go through this material. There are more details here, and there's one question at the end that you can try to answer based on this material.
We come to the third episode, that is what problem fits to GPU. We have the instructor Pedro from UMIL. It works as a application expert at HPC Twin.
Yes, I will talk about what problems fit to GPUs, right?
Yeah.
And here there are the questions that we will cover in this lecture. So the strengths and weaknesses of the GPUs, the tasks that are suitable for GPU computing, and specifically this is important this time, GPUs for machine learning applications. So in Stack Exchange, there is an analogy of how the GPUs work. And they make the comparison with a bed of nails, right? So if one lies on a bed of nails, yes, and all the nails have a regular pattern, they are well aligned, then one doesn't feel anything, right? And this mimics the behavior of a GPU, right, where there is some evenness that should be achieved in order to get a good performance. On the other side, a CPU could be seen as a bed of nails where the nails are spread, yeah, right, and they are not uniform. So these are some of the problems that are suitable for GPU computing. And you can see here large scale matrix and vector operation. And you know most likely already that in machine learning, we have a lot of these type of operations, and machine learning is based on these linear algebra operations. and they can achieve a good performance of the GPUs, yeah, because they are a lot of them, right? And these operations can be parallelized efficiently. Also, Fourier transform. There are also common to several fields, machine learning, computational chemistry, for instance, fluid dynamics, image processing. This is a broad range of areas. Yeah. Monte Carlo simulations, they can be used in economics, physics, and other fields. Molecular dynamic simulations that are common in several areas: chemistry, biochemistry, biology, computational fluid dynamics, where plenty of linear algebra operations are involved. They can be run on GPUs efficiently. Convolutional neural networks, right? As we discussed previously, because they involve also linear algebra operations, big data analytics, and graphics rendering. Notice here that this was the original purpose of GPUs, right? To render images in video games, for instance, in a very fast manner. So the GPUs are also not that good or not suitable for some tasks. Not all the tasks can be run efficiently on the GPUs. And here there is a short list of the possible tasks. For instance, a sequential task where there are some dependencies between the next steps and the previous steps, right? And some algorithm require this sequential workflow. So this is not suitable for GPUs, because remember, you need to have some highly parallelized algorithm. Yes. Also, fine-grained branching. If your code is using a lot of if statements, and here an example can be, for instance, the quicksort algorithm to order the elements of an array according to its value, right? So the original algorithm, it involves if statements, and in that form is not suitable for GPU computing. Also, low arithmetic intensity operations, yes, where you only perform a few arithmetic operations, and you need to get some data, right? So this is not suitable. Also, small data sets, where again you have some data to be transferred and few operations to be performed on the data. And this data needs to move back and forth between the GPU and the GPU. And previously we saw that this transfer of data between GPU and CPU is costly. Limited parallelism. Some algorithms have an intrinsic limitation in the degree of parallelism that can be achieved. And because of that, they could be not suitable for GPU computing. And if your algorithm requires a lot of memory or data transfer, then also this could be a limited factor because of the bandwidth between the CPUs and the GPUs. So, but this is not a strict list, I would say. And in general, if you have an initial algorithm that performs well on the CPU, then you need to change your style of programming or your mindset to make it a more appropriate for GPUs. For instance, in the case of the sequential task, where a previous step it depends, or the next step depends on the previous steps, then you can find some new algorithm that avoids this procedure, and instead you come up with a new algorithm that is more parallel. And some of these steps can be overcome if you change the style of programming. And also, most likely, if you make some approximations on the physical problem, and you take into account other factors. So this is an example of a GPU acceleration, in particular in the Julia language, right? So Julia has support for several types of GPUs, including NVIDIA. And in this case, this example shows how to use AMD GPUs. You need to install the AMD GPU package, right? And the nice feature of Julia and AMD GPUs package is that you can write your own kernels if you want. This package has support for writing your own kernels as well. So here you can do a performance analysis using these benchmark tools in Julia and see how the speed up is in this short code. Notice that the changes that you need to make to your code are small, I would say. So for instance, here you have an array, yes, a two-dimensional array. And in order to run on the GPUs, the only thing that you need to do is calling this function from the AMD GPU, and this will put the array on the GPU side. So if your code is using this type of operations, then you could get some speed up on your code. So these are some examples, yes, taken from the literature about the applications of the GPUs. And in particular, in this field, electronic structure, the GPUs has been used or has found a niche, right? And they were applied from the beginning, yes, of the GPU usage. So in this case, we show the performance of the BASP, which is a package for electronic structure calculations. And you can see here how it performs when you move from one node to two nodes up to 16 nodes. And this was done on the NVIDIA GPUs. So in general, these packages for electronic structural calculations have been ported to NVIDIA GPUs, and they are also ported gradually to the other GPUs like the AMD GPUs. Here you can see the energy efficiency of the BASP. Yes, for different type of systems, yes, compared to the pure CPU case, which is the Corey Haswell in this case. Computational chemistry is also a field where you can apply GPUs in an efficient manner. And this here, I wrote an algorithm that is well known and using computational chemistry calculations. This is the basics of some of the more elaborated methods. This is Hartree-Fock. And you can see here that several matrix operations are performed. And if you write down the equations or you transform this into a code, you will see something like this. That this is quite common in computational chemistry codes. The important thing here is that you can rearrange the loops and also perform some symmetry operations to compute these integrals, right? And in that case, you can achieve a high level of parallelism, and because of that, only by converting this loop into a highly parallelized loop, you can achieve a good performance even with all codes such as the one written in Fortran. So these fields, computational chemistry and in electronic structure calculations, yes, the GPUs were or have been traditionally used, right? Also in molecular dynamics. But there are also new or novel areas where the GPUs are being used, and these were not traditionally seen in the HPC environment. And some of them are in the humanities, right? And here people are using, for instance, the large language models and neural language processing, where they use these tools to analyze large databases of text, right? To get some information about that. Also in archaeology, right? People take videos or pictures of the excavations, and then they try to analyze that by using machine learning, deep learning models, and they need the GPUs to accelerate these calculations. In cognitive science, and this is just one example, people are using Markov chain Monte Carlo to analyze several behaviors or in population and dynamics. So here there are some exercises that you can discuss during the hands-on session, right?
So first, I apologize. I think I did not introduce myself. My name is Christiana Kim, and I work at CSC, which is the National Computing Center of Finland, in the user support group, where I help users with I assist users with using the GPUs, and also try to give some advices about how to map their problems to our machines. And also we are involved with some porting projects from CPUs to GPUs. So CSC owns 2 supercomputers in Finland. It owns 1/4 of Lumi, and which is also, but that's also hosted in Finland. And so we see that GPUs are, the power of GPU comes from parallelism. And in order to use GPUs efficiently, we have to understand how, we know we have to create many threads, but we also need to understand how are these threads executed on GPU, and how is the execution linked to the hardware of the GPU. So for some background, so we see that from the point of view of hardware, we have two types of architectures. We have these so-called distributed memory machines, where we have processing units, nodes, which are independent of each other. They have their own memory, and like when we have a parallel problem that is divided in smaller parts, if we need to have some kind of communication between these parts, then we need to, some network is needed to actually communicate from one of these processor unit to the other one. We also have here, we see on the right, this kind so-called shared memory architectures, where all our processing units have access to the same memory. So the data that stays in this memory, it's actually can be read and modified by all of these processors. So, sorry. So in this regard, the GPUs are closer to this kind of shared memory machines. So we have many cores which execute threads in together, and they try to solve a problem. And now this problem resides on this global memory, and all of them can actually read the data, and they can modify this data which is in the memory. So now, depending on this hardware layer, we need to use process-based parallelism or threads-based parallelism. So process and threads are similar. They are execution units which are processing some set of instructions in the specific order. But processes are, in a way, heavier, and unlike threads which share the space, they have their own memory space. So one process we see cannot see the memory of the other. So for distributed memory machines, this is the only way to program them. And then when the time comes and some data from one process is needed by the other one, then we have this kind of message exchange, and they can then go on with the computation. These processes are created at the beginning of the programs, and in general, they are alive until the end. So that's the processes have the lifetime of the program. For shared memory machines, we can use this kind of thread-based parallelism, where we create and destroy threads when it's suitable. So in this case, for example, we see that we would have an application which does something here, initializes the system, and then reaches a point where there is some heavy computation. It spawns some threads, finish the job, and then after that destroys all the threads that are not necessary and continue the execution. So GPU execution model fits in this model, but the difference from this diagram, which was made for the CPU threads, is that we don't have just a few threads, we have thousands of threads. So because you also have much more computing elements in a GPU. And there is also some way that these threads are mapped to the hardware, which is to be different from the multi-core CPUs. And when we have a problem, we split it in parts which are independent of each other. They can be solved independently up to some point when we have to do some communication. But we have two types of exposing parallelism. One of them is like this data parallelism, in which, let's say we have an array, data 1, and we want to apply on each element of this array the same operation, which is called func1. Here we have another array which does the same. So this kind of parallelism is actually the one that fits the GPUs. So GPUs, in order to use GPUs, we have to expose the parallelism in our program by using data parallelism. The other type of parallelism is called task parallelism. So this is used when we have applications that they have different operations. So for example, if you would do some cooking, then you could say one task is cutting the vegetables for the salad, and then the other task is grilling the meat. These two operations they can be done at the same time. Of course, we have to balance them correctly so that they finish at the same time. In real life, we see quite often task parallelism in the climate modeling applications. So usually they have different components. So we have air, ocean, lands, rivers, and each of these can be it's a specific task, it's a different task that we are solved separately, and then at some point they have to communicate and they exchange the data. So GPU execution model fits into this shared memory category, and in order to use it, we have to employ a thread-based parallelism, expose the parallelism in the application by using this kind of data parallelism. But there is another thing that is very important for the GPUs. Unlike the CPUs, GPUs are meant for high throughput. So we have to, this is in a way similar to a multi-lane, very broad highway, where we have lots of small machines which they all go in the same direction. There's not much flexibility, they go slow, but if you would think the rate of how many machine passes is very high. While the CPU is a very narrow road, but we can go very fast, but have much fewer machines going by like threads, but they are more flexible, they can go very fast. But how is this done in practice? So first, we can check the GPU execution model by actually looking at the problem. So for this AXPY, it's a very good example. So if we have two arrays, y and x, we want to multiply the x by some scalar. So each element of x is multiplied by this, and then we want to add each element from this a times x to each element of y and store it back into this variable called y. So on a serial CPU, you just have this kind of function. So we have a loop, we have this index ID, which go from 0 to n minus 1. So this is C, so this is how the indices go. And then for each value of ID, we have this kind of operation. We can see, of course, that each of these iteration is independent of each other. We can have any order for this, and the result will be the same. So this can be done in parallel. Now, on the accelerator, we have no loops. Well, we have loops, but let's say we don't go over all the elements. But in this case, we can eliminate totally the loop, and then we can define this kind of function, kernel, and this kernel is written from the point of view of a thread. Each thread, in this case, does the same operation. It takes one element of this array, and then it adds to it this a times the x corresponding to this ID. So now when you want to solve this problem, AXPY, we just have to tell the GPU, run this kernel for all possible values of ID. And this is called a grid of threads. And this is what we send to the GPU, which then processes this and gives us the result. One thing about these threads, which are in this grid, is that if we take randomly some threads, it is not possible to really synchronize them. They have to be, there is some limited synchronization that can happen. But in general, we should not base our program that we can actually synchronize random threads. So now, as I said, we have many threads, and they all execute this kernel. So when the computation happens, then we can say that one of these CUDA thread is mapped to so-called CUDA core, and each of these thread has their own state and their own private variables, but these threads are different from the CPU threads. They are much lighter. They can be, there is very little cost to create them and to destroy them. So that's why we have so many of them. That's why I have so many of them. And then every time we want to solve a problem, we have one kernel launching, and then for the next kernel, we create again threads, and they execute they do the processing. But these threads are not independent of each other. So there is some kind of hierarchy to the threads. And also this hierarchy is because of the way the hardware is built in the GPUs. So these cores are not independent. So actually what happens is that we have the cores. The CUDA cores are grouped together physically, and the idea is that when some kernel is being processed, all these cores, which are in this SIMT unit, they have to do the same operation. And all the threads that are assigned to these registers then are actually locked together. They have to do the same operation, the same instruction. So it will be a loss in performance if you'd have branching here, like, for example, even index threads do one operation, one thing, and then odd index threads would do something else. And a very important detail, the memory accesses of the threads, it's actually done by the whole group. And so, for example, if this thread to the left requires some data, then it's not just going to trigger a fetching of one element of the data, but it's going to trigger actually a block, which is 32 bytes, 64 bytes, or 128. I'm not sure if there are some other sizes. So in the ideal case, the threads that are in this warp need this data, and then you only need one memory transaction to access this. If the algorithm or if the code is not written well, then of course the efficiency of the code will start to decrease. You'll get less performance. Some other things we see here. We have is in the SIMT unit we have these registers. So these registers are like a type of very fast memory, and each thread gets a few of these registers where it stores their own internal variables. And we want to keep the operations that are done by each thread small, light, so that we don't fill up these registers. If we fill up the registers, then we start to end up in trouble. There's something called spilling happens, and then slower memory is used, and you will see the performance drop immediately. So the size of this group of threads, which are called warps by NVIDIA, it's 32 or 64, and I think that Intel also has. I don't remember. I think Intel it's either 32 or 64, not bigger. So it's very similar in this regard. And now there is another hierarchy to this grid of threads. So physically, so the chip, the hardware, we have these SIMT units, and we can have one or more. In this case, like the AMD GPU, now they have 4, and they are grouped together in so-called streaming multiprocessor. Now, what's different here is that now here there is a very small amount of memory that they can be shared by the threads which are running on these SIMT units, and this memory can be used to communicate between themselves. Also, this streaming multiprocessor has some extra control layers. So all the warps that are running, that are part of a specific block, then we can have inside this block a synchronization, though not with other blocks. And also, as a consequence of this, since the blocks, the grouping of the threads in warps and blocks is because of the hardware. A block is created when the kernel is launched, and then it's assigned to one of its SMP. And then it cannot be splitted, cannot be moved to another SMP. It will be active, it will stick to this SMP from the beginning of the kernel all the way to the end. These SMPs allow to run more than one block, but still, even if the two blocks run on the same streaming multiprocessor, they cannot exchange any kind of data, and again, they cannot be synchronized. The synchronization can only happen inside the block of the data exchange. So when you try to solve a problem, you create a grid of threads, lots of threads. So, for example, here we have a problem size 4096. So we need to assign to each thread a specific part of the data. So this index is ID that from the kernel. Here it's index. We want to instruct the threads that you have a specific index, a specific element of this array. So we can extract the index of the thread, and then based on this index of the thread, we can assign a unique index in the array. And we have this so-called these intrinsic variables. For example, this grid dim, it's giving us the total size of the grid of the threads. And of course, the threads are grouped in blocks. So each block has its own kind of index, starting from 0. And then inside the block again, we have another variable which will tell us the coordinate of the specific thread inside of this block. So based on this, we can create, for example, if we take this orange thread here, we can create a global index of a thread. And based on this, we can assign that it works on the element of the array which corresponds to this index. So in this case, we take for this orange thread, we take the local index inside the block, which is 3, and then we add to it the number of threads which you have up to this point. So this is the block index, which is 2, and then the size of the block, which is given by this intrinsic variable block dim.x. So in this case, this orange thread will actually work on the index of the array 515. Now, again, we have 3 GPU producers, and then we also have several ways to do parallel programming with GPUs. And they share lots of things, but still they use different terms for this. So in AMD and NVIDIA GPUs, we create a grid of threads, but in OpenCL, in SYCL, this is called ND range. When threads are grouped in blocks, in SYCL they are called work group. We also have in OpenACC gangs. In OpenMP we have teams. Then we have this very important concept of warp. It's called subgroup, and so on. We have this shared memory, which is on an SMP, which is very important for optimizations. SYCL call is local memory. So don't confuse it with this local memory that here in CUDA and heap, it's actually referring to just the variables which are specific to a thread. And of course, when you do direct programming of a GPU, we have all these variables which are provided by the language that we use, and then we can get all the coordinates of our threads in this grid of threads. So as a take-home message from this episode is that GPUs are shared memory type architecture, and we have to use thread parallelism in order to use this. We expose the parallelism using data parallelism, so we practically, if you have an array, we process all the elements in parallel, and all of them, they are practically doing the same operation. Because of the way the hardware is organized in the GPUs, the threads also have like a hierarchy. These threads, physically, they are locked in small groups called warps or waveforms. And the idea is that all the threads in the warp have to do the same operation. So we should try to avoid branching inside the warp. And also the memory accesses are done per warp. So we need to, when you have a program, we have to think about how the threads can, which are part of the warp, what memory do we access? And if that's coming in one memory transaction by loading some block from the memory, or do we need more than one memory transaction? Thank you. So there are some questions here that when you have time, you can revise the material and then try to answer these questions. Basically, a summary of this material.
Good. So I will go over some most popular of the multiple programming models that exist, and most of them you will hear about in more detail in the next day and a half. So the first question when one wants to solve some problem with GPU is whether you need additional programming at all, because there are ways to use GPU for computation without doing the programming. In best case, the code has already been written, and you only need to set the parameters to launch it on a specific GPU or GPU architecture. In some other cases, one has third-party libraries developed that do all the GPU offloading and porting under the hood, and then again, the end user can simply benefit from that. For example, this is increasingly the case with machine learning on Python. If you use PyTorch, you may not even know that it's doing something on the GPU, except for when you notice the speed benefits. However, especially in HPC, so-called traditional high-performance computing, it's still very often the case that one must port their codes to the available architectures, GPU architectures themselves. And for that, of course, you will need some additional programming. So, as I told, there are a lot of programming frameworks to the point that it is quite possible that you won't find the one that you might have heard about not listed here. But we will stick to at least some popular and common ones, and instead of going through the alphabetical list, I would probably group it in four broader subsets of programming frameworks and methods, namely directive-based models, then kernel-based models, which can be non-portable, so vendor-specific and portable, so vendor agnostic, and then some attempts at supporting GPUs through high-level or even language-level approaches. Starting with language-level approaches, both C++, and Fortran being very old and having some history in high performance computing, they also have some initiatives to support GPU hardware on a language level. So they even put it in the language standard. The links provided here in this section are for NVIDIA, but I think there are equivalent initiatives from AMD and from Intel as well, which is to provide parallelism support for standard libraries. And that parallelism can include both generic CPU parallelism as well as GPUs. So, for example, if you take some sorting algorithm or reduction algorithm from the standard library, you can make it run on parallel CPUs or on your GPUs associated with your main CPUs. And you can look up the articles from NVIDIA there, and then if you want to use, if you want or if you have to use AMD or Intel hardware, you can look that up further. The first broad group of GPU programming models would be directive-based programming. There are main two flavors, so OpenACC and OpenMP. And in this case, in directive-based case, one takes the existing serial code and annotates it with hints, pragmas, or directives, indicating to the compiler what has to be parallelized or offloaded. In case of OpenMP, that was started as a CPU parallelization, but by now it also supports GPU offloading as well. If there is no API or no compiler support for the directives, they are treated in the code as comments, and the code can be safely compiled as a serial code without the benefits, but also without needing to rewrite the code to account for multiple CPU availability or GPU availability. So then this allows you to employ the hardware that you have with minimal programming effort. And the parallelism is then done in steps by adding comments, directives to those sections of code that can be most trivially parallelized, and then adding additional effort or work to refactor the other sections of your code that would still benefit from GPUs. I mentioned two main flavors, so those being OpenACC, which is supported by main GPU vendors, and OpenMP, which has started as a shared memory parallel programming API model, but by now also supports GPU offloading, which means running parallelized code, directive parallelized code on GPU hardware as well. In both of these cases, as you will see in the afternoon, it's not necessary to write kernel functions directly. The compiler does that for you. So the advantage is that you don't need to be intimately knowledgeable with kernel writing. The disadvantage is that compiler can make a good work, but probably not the most efficient work. So you may lose some performance over convenience. The other broad group of GPU programming models, or maybe the one that is the oldest and in some ways most used, at least in the early stages, is non-portable kernel-based models, which means that the graphical processing hardware vendor also provides the low-level libraries or API to execute function kernels directly on their hardware. Theoretically, this then gets you the ability to use the technology in the most efficient way, in the most direct way. The drawback being that you have to learn the specific language of the vendor to be able to write such code. So the first and the oldest is CUDA by NVIDIA, And it looks like something like C-like code, and then the syntax is very similar to C. And then you can combine that through a special compiler with either C or C++ code, compile it and run it. CUDA also has bindings in multiple other programming languages. It has probably the most extensive ecosystem, so examples, research, blog posts, whatever, of all possible non-portable models, but still, again, CUDA directly works only on NVIDIA hardware. If you wanted to use it on AMD or Intel or some future thing, you have to do some additional steps. One of those additional steps done by AMD is HIP, so Heterogeneous Interface for Portability. It's AMD-specific API also to provide low-level interface equivalent to CUDA. It's also based in some part on CUDA, and at least theoretically it should work on both AMD hardware and NVIDIA hardware. If you're interested in the direct examples of non-portable kernel-based models, you can find examples in the teaching material directory. The link of it is there, and the two models, so CUDA and HIP, also will be covered in later sessions of this workshop. The third broad group of GPU programming models are, again, kernel-based, but in this case, these are the approaches that try to unify the application programming environment interface for all possible vendors, so that you could write a single source and then compile and execute it on all kinds of hardware, whether it is NVIDIA, AMD, or Intel, or even some future thing. Some of the notable cross-platform ecosystems are OpenCL, probably the oldest one, SYCL. Then there are some newer names as Kokkos, Alpaca, Raja, and the list can go on. So what do they do? Let's start with OpenCL. So OpenCL looks to be a cross-platform open standard API for general purpose parallel computing, and it claims to support CPUs, GPUs, and FPGAs. What it does, it also provides a low-level programming interface. However, it adds additional abstraction layers, so instead of writing precisely CUDA-style kernels or HIP-style kernels, you write so-called OpenCL-style kernels. Also, OpenCL as a project, they don't develop their own implementation, so you can get OpenCL SDK from the hardware vendors actually as well. So AMD and NVIDIA both support OpenCL, writing their code that works on their GPUs in OpenCL as well. Another alternative would be Kokkos, another portable programming model. It's based on C++. It again, similar to OpenCL, it provides another abstraction level to write kernels that would then be translated to any underlying hardware. It is made of several components, the first being Kokkos core library, then Kokkos kernel library, that already has kernels, for example, for linear algebra and some graph algorithms, and then additional Kokkos tools to profile and debug programs written in Kokkos and then being launched on different types of GPUs. Kokkos also claims to integrate well with other software libraries, including CPU parallelization, such as MPI and OpenMP. And the third framework I will touch upon is SYCL. So this one is tied to C++. And Similarly to the two previous, it also aims to be a portable programming model for multi-device programming. Originally, it was developed on top of OpenCL, but I think by now it is separate framework by itself. It is implemented again on top of low-level APIs such as CUDA or HIP, but SYCL programming then again does not need to know specifically about CUDA or HIP kernels. They still need to know how to formulate and write SYCL kernels, SYCL objects. In contrast with frameworks like Kokkos or Alpaca, which are specific project, SYCL is given as a standard. So again, similarly to OpenCL, there can be multiple implementations of such standard of SYCL. And one is provided by Intel, specifically one API, DPC++, and the other is Adaptive CPP, which changed names a couple of times. It was known as HipSYCL, then OpenCL, now it's supposed to be Adaptive CPP. This one is nice because it claims to support NVIDIA and AMD GPUs and also experimentally support Intel GPUs. There are also other SYCL implementations. So in summary of portable models, they do require you to learn some style of function kernel programming. So basically to know the concepts of the GPU hardware and then apply them in your in the factoring of your code. But they aim not to be dependent on specific hardware vendor, so that it should not matter whether your system is AMD or Intel or NVIDIA. And then there's the last section on high-level GPU support. So I already mentioned standard support attempts or initiatives for C++ and Fortran. Some increasingly popular solutions for that are from the languages of Python and Julia. So Python is an interesting case because, at least historically, Python as a language was used very often as a glue that is combining, for example, different parts of HPC computations, maybe in different languages. But of course, by now, there are initiatives to make the high-level language level or library level GPU usage implementation in Python too. So because of that, and because of the fact that Python programmers usually tend to split multiple projects and work differently, there are also Python libraries or Python projects that cover different abstraction levels. On the lowest level, it is possible to use Python language as a direct wrapper to the CUDA or HIP kernels. So NVIDIA supports CUDA Python project, AMD has their own HIP Python, and then there are some community supported projects, for example, PyCUDA. All of them seem to provide Python bindings to the low-level APIs. And what that means usually is that you can use all of your instrumentation or analysis or setup code in Python, and then give the data from Python to the low-level implementations to work directly on the GPUs. Also, in that case, one would need to know the syntax of the low-level GPU programming too. CUDA Python, at least by now, is starting to aim to provide support for other toolkits and libraries that are slightly higher level, namely, for example, CuPy and NumPy. So CuPy is a library that aims to support the the execution equivalent to NumPy, but instead of CPU acceleration, to port it also to GPU acceleration. So it offers highly similar interface. Code written in NumPy can often be adapted to use QPy and then to benefit from the GPU resources with minimal modifications. In most straightforward cases, it may be possible just to replace NumPy with QPy and SciPy with QPy x SciPy and run your code, and your code is offloaded on the GPUs on the spot. In some other cases, or if you want additional performance, one might also look further in writing their own kind of kernels as well. Other project that started as optimization on some other part, but now is providing optimization or offloading for GPU hardware as well is Numba. So it started as just-in-time compiler, and it's still just-in-time compiler. It can translate a subset of Python code and NumPy code into optimized machine code. First of all, optimized CPU code, but by now it also supports CUDA-capable GPUs. There was some AMD support previously. It was removed from Numba, and at least now officially Numba does not support AMD anymore. And one of the particularities of Numba is that by using Numba, one can actually use slightly different variants of syntax. So there are decorators like GUFUNC that can make use of GPUs implicitly, or you can, using Numba, also write a kernel similar to the CUDA kernels explicitly. Julia, being a newer language and designed already with thinking about optimization and optimization on modern computing architecture, has from the beginning had first-class support for GPU programming. So it has specific packages that target GPUs from all three major vendors, and in most cases, the porting from one vendor to another consists of changing some names from AMD into one API or to CUDA. In the examples, you will be able to look at the examples more. I think it's tomorrow for high language models in more detail. So these packages from Python and from Julia, they offer they might offer some higher level abstractions that require little programming effort, and then also add a possibility to go for a lower level approach to get more performance and more control on your GPU execution. To summarize the possible programming models, everyone has their own strengths and weaknesses, and basically your choice will depend on what you want. What hardware platform are you planning to support or you have available for you? What type of computation would you like to perform? And also, what is your style of coding, your experience as a developer, and your preferences? So, and then the choice may fall somewhere between the high-level APIs that are focused on productivity, writing the code that just works, and lower-level performance-focused APIs, which then would result in faster execution, larger problems being able to compute in the same time or on the same machine. But, of course, at the cost of more coding effort and more expertise. And at this point, I would like actually again to start the 10-minute discussion on which programming frameworks have you already used previously, if any, and some experiences of what you found easy or hard, what was most challenging, what was most useful for you in trying out one or another programming framework for GPUs? Please write your comments into the HackMD.
Good afternoon. Welcome back to our GPU programming workshop. During the next 80 minutes, we will go through a very brief introduction about directive-based models together. The most common directive-based model for GPU parallel programming are OpenMP and OpenACC. The parallelization is done by introducing directives in places which are target for parallelization. However, there are some difference between these two. OpenACC more descriptive. That means the compiler could be help you to a lot. But for the OpenMP overloading, you need more explicitly tell the compiler how to parallelize the code and so on. So in the OpenMP or OpenACC, the compiler directive are specified by using this sharp pragma in C or C++. But but for Fortran, there are some special comments identified by unique things. The compiler can ignore these derivatives if the support of OpenMP or OpenACC is disabled. These compiler derivatives have various purposes. For example, or create threads, or make the work sharing, or manage the data environment, or maybe synchronize the work among these threads. For the execution model, OpenMP and OpenACC both use a fork-driven model. The program begins with a single thread execution. The master called master threads. So everything is executed sequentially until meet the first parallel region. When the parallel region encountered, the master threads group of threads become the master of these groups of threads, and find the thread index with 0 for this group. There will be a implicate barrier at the end of each parallel region. So now we coming to this offloading directives. First, we start with OpenACC. The most common used directives is the kernels, which define the region for transfer the series kernel into executions on GPU. The work sharing is more automatically by the compilers. Here is our first example. For both C++ and Fortran, we have these tapes. You can choose between them. Depends on which programming language you are more familiar with. So now we could start our first hands-on session. So on the HackMD, there is a section we write down here to help you to prepare the setup for the hands-on for these derivative-based models. So after you log into the Lumi, you could start with a modular.
Wait, can you zoom in a little bit? Or it's a little bit small.
Cleaner. Let me try.
Yeah.
That's a bit big.
Yeah.
Larger.
Much better. Yeah.
Okay. So,
probably you can tell us how to get access to this lesson material or to these accesses.
Yeah.
Using the
But
gate.
the access we use are most on the training material online.
Okay.
So for other access, maybe used in the following days. I can do a short introduction. After you hit alone, our GPU programming repository to the local, you will find this folder called GPU programming. So in the GPU programming folder, in the contents and the examples, you will find most of the examples.
Wait a little bit slow,
Yeah.
because you are switching too fast.
So let's go back to git clone the repository. So I already have this on my folder. So inside this GPU programming folder, there is a content and examples. So everything used for the hands-on access for this programming workshop are here. So let's use CD to change into the folders. Yep. But for this section, we will use some setups. Let's do the first modular purge. We remove all the modulars already loaded. Make sure everything is fine, and later on we load all these modulars. We could use ML to check all the modulars we loaded. And we could create a folder, for example, demo. So I already have inside. So we can change into the folder. Let's remove everything. So we can you can use any editor you want. Now I use Vim to create the first ACC example for the Fortran. Oh, sorry. Oh, here I want to mention for the OpenACC examples, on the Lumi, the curly compiler only support for the Fortran, not the C++. But for other system with NVIDIA compilers and NVIDIA hardware, the C++ and C are supported. But here we only demo the OpenACC with Fortran examples. But first, let's try this kernel directives example. We can copy the code. save it. So on here, the instructions have the list, have the example how we compile the code for the OpenACC. So we have the executable. Now we need to allocate the GPU resource to for run this example. We have two ways with the interactive or allocate the resource and run with the srun. So let's try this one, the sloc. We require one GPU with 8 cores. The time limit is 1 hour. I think it's enough for this this session. With the partition Smart-G, probably we could share the node with other users. We could use srun. Oh no, sorry, srun to launch this program. Yep. So no return or screen print. Here we could print more debug informations to see what is going on underneath. That is the export this environmental variables. Let's launch this executable again. So we could see there are some OpenACC stuff underneath, like allocate memories and transfer and execute kernels, free the memories. So this code now is running on the GPU. So let's come back to the example. What we ate for the code is only 2 lines with this directives kernels. It seems very simple. We can offload the big loop onto the GPU, and the compiler will do all the stuff. If it works fine, it makes the work sharing for the loops with a different index, or everything is running parallel on the GPU. So I think this is a good start for the derivative-based model. We can see it's very simple. Everything is just like 8 comments for code, and tell the compiler these regions we want to run parallel on the GPUs. Next, we have other derivatives besides this kernel derivatives. We could use parallel to make more explicit offloading. But the parallel derivatives will not do the work sharing after we add another loop derivatives to achieve the whole parallelism of running the code. So in the next few minutes. Let's do these demos by yourself. For the parallel loop derivatives, let's see if you could run this example successfully. I think everything are same for the code except this two line. Yep, let's start. So if
Wait,
you
probably you can
have
show us.
questions,
Yeah, probably you can show us the in the terminal about the history and how to get clone and how to get access to these materials, because you type at the terminal somewhat too fast.
and people ask questions on I can do.
No, just the history is okay because we need to.
The history will list too much. Yes.
We'll come to the bottom of this material. I can leave a few comments for you to run the handle accesses. A better way is that you come to this directory, come to scratch project and this number and create your own directory right there and then git clone these materials to your directory and then to play code right there.
And the other possibility would be, because most of the files are actually written down explicitly in the teaching material, so you can look at the sections and you can copy and paste the relevant files. So let's say OpenACC on C, or OpenMP on Fortran, or OpenMP on C++, and then just create the files here and then on the cluster and compile those like this. So example files are available in the teaching material, but they are also written out in the web page as well.
The Lomi workspace will show you the where you can access or store the files. We have this scratch project number. So we can go here. Let's say create a folder with your username. So I already have. And here you can make the git clone. Let's accelerate this. example, copy the code into the file with the same.
When you are switching too fast, probably slow down a little bit. And
Yes.
when you use double screen, means the upper is the terminal, the lower is the web page, so that the participants can get a clear image where you copy and where you paste.
That's fine.
Yeah. Yeah, this is good.
Yeah, here's the example. The compile code, substitute the name of the file and the executable you want. With the s run. Yeah, they do stabler thing. Let's show the parallel loop could do similar job as the kernel directives. I think these examples should have no problem to run. So let's give you a first taste about this directive-based model for GPU programming. With a simple way. For the OpenACC, there are many levels of parallelism for loading execution. I think in this workshop later on, they will introduce the details for this. For this CUDA programming model, we have this thread blocks and all these kernels in grid. For this OpenACC, we have some clauses could control for how many threads in the block and how this grid are launched. So these derivatives to control different parallelism of the levels could help you to tuning the performance. We will not cover in this short introduction session, but you could go back to here to think a little bit more. There are like a number of guns and number of workers and vector lengths. These things could launch or generate the kernel mile suitable for your GPU architecture and meet the resource limited by the GPU. So you have more control about the kernel generated. Next, we will have a look about OpenMP offloading. The first derivative for OpenMP derivative is target. But we need to notice that the target directive is not equivalent to the OpenACC kernels. This will not do the parallelism underlying the loops. This only tell the compiler this region are for the GPU offloading. There are other derivatives to make the thread creates and make the work sharing, like the team distribute, parallel do, or for Fortran and the parallel for the C++. Also the SIMD. They also have other clauses like number of teams and the thread limits help to generate corresponding kernels. In the OpenMP 5.0, there are new loops. These things are more similar to the kernel, so let the compiler to help you to generate the parallel code. So there are tables mapping different terms for OpenACC and OpenMP, and also corresponding to the NVIDIA and the AMD GPU. So the next hands-on access, let's try this OpenMP target team distribute parallel do SMD derivatives to make the big loop parallelized on the GPU. I think the commands are pretty similar as before. We could do it now in the next few minutes. So these examples with a smaller loop up under, the execution is very fast. You can change these values to see the difference for running on the GPU. So besides for that, we said we can disable the GPU offloading and with the same code run on the CPU. Let's try these examples. So with this ACC, we change to OpenMP. So for consistency, let's remove move. Use fpn to compile code. Let it know it's the OpenMP with the name of the executable we want to generate it and the source code. Let's run it. Now we try to demo how to compile code and run on the CPU. Let's delete this HOMP. It's give some warning. Yeah, but it's that just ignored. That's without this HOIP flags. So the compilation contains OpenMP derivatives. This OpenMP is not active, so it are ignored. So with the same code, we can run it on the CPU. I think we could run it directly. We didn't see any debug information about running on GPU. So the same thing, we could turn on the OpenMP offload supporting. So maybe people could play with the index, change it to a larger number. Recompile. Use time. Feel very fast. Anyways, these examples only let you have a taste about the derivative-based model. See how it simply can make your code to run on GPUs. So next session, we will come to the data movements. So why we have this data movements? Let's see this figure. Usually on the system, you have so-called the host and the device part. The host contains the CPU and the memory and could be accessed directly by the CPU. But on the device, the GPU, they have its own memories. So when we do the programming, we need explicitly transfer the data from the host memory to the device memory. this transfer will take times. If this transfer happens frequently, there will be consume a considerable amount of time, make the code a little bit slow. And we can see the compiler helped this data transfer by itself. When we run the code. Sorry, and any question? We can see it's generate data copies and also the kernels, and we see it's transfer a lot of data, and after execution is transfer the data back. But for this example, we only need read to memory on the GPU side and transfer the initial value to it, make the addition and save into the array vector C, and the result we want probably only in the vector C, and these two array on the GPU side we don't need it. So we could reduce the state transfer of these vectors, or we should avoid that. So how to do that? The data movement directive could explicitly cite these copies and transfer. So we have a copy in, copy out, create arrays and delete arrays. So let's jump this structured and unstructured data region. Let's see the example first with the data mapping courses explicit. So let's do the one with OpenMP and Fortran, or you want to try, you can do the C++ example. Let's see the difference in these examples with data mapping. So you're supposed to add some courses here. But let's look the solution.
O, fajno, da je povedal enkrat neki, no.
Sorry. So any question? No. So we see here they copy the vector A and B to the device, and after the execution or addition here, we only need the vector C to the host from the device. This example contains the mapped derivatives explicitly control the data movement, and the one we did before without this data movement. Let's see the difference. We saw it's oh, sorry. The example we changed. Let's see here, without this data mapping, we have 3 copies, A, B, and C. So we can we use the map only map the A and B to the GPU. It's reduce a lot of copies and allocate the C only on the GPU. So for this example, we saw we have the freedom control the data creation and the data transfer, and this potentially reduce the running time, and this could be the key for tuning your program. I think the most important is only do the necessary data transfer. So now let's jump back to the online material with this structured data region and the unstructured data region. So you could have this target data derivatives, and in between with a series of code which you use OpenMP offloading, and it manage the data for the code in between. So that's easily do when your code is one file. But sometimes you could use this entry and exist for the unstructured data declaration. So the key point here is start and end points within a single subroutine. The memory is only exists with the data region. So when you have multiple start and points across different subroutines, this unstructured data region will be help a lot. And the data memory exists until explicit delocated. So when you meet this directive, obviously exist. And there are also sometimes we need another derivative called update. It used to synchronize the data between the host and the device. That means they both already exist on the device and the GPU. The update make this synchronization. Oh, here is an example. For the OpenACC. So after you copy the data, to the device, and you make a new assignment on the CPU side, and you could use update to make synchronize the value on the device for the X. And here is the end of data structures. Everything come back. So this will be easy to understand in the checkpoint 1. After copy, and they should be same value on the device side and the host side. But here is only two on the CPU side. We see on the host side it's 10. On the device side, it's not updated, still 0. Until we explicit update the device, it becomes same. This will be very useful when you have such a scenario. The good thing about the directive-based framework, we could incrementally do the GPU porting for your already exist code. They have the same code could be compiled on the CPU and GPU with the compiler flags, and it have a relative low learning curve. And with the compiler helps, you don't need to know a lot of low-level hardware details. So it have a good portability. So in this short and brief introduction, we only cover very less about this OpenMP and OpenACC, and many other complex situations and performance related tuning stuff. you could have to read our lessons about OpenACC and OpenMP. They have more details about these two. I think all the introduction part is done now, and people could play with these simple examples, make some experiments, and ask questions.
Okay, so first a comment. You will see another example of data entry, exit, and update clauses in the example on the third day of stencil computation. And also, is it okay way if I put my if I do some demo with my perspective on this, on directive-based programming?
Yes.
Okay, so I would be focusing on OpenMP on C++ because this is what I know best.
Yep. So you take control now?
Yeah, I will.
I stop share.
Okay.
Thank you.
So what do you see on the screen? So now I'm sharing my screen, and in fact, what I have here is a web interface to Lumi. So the same thing that you can access via SSH. Since recently Lumi also allows to do many things over web interface, the dashboard, when you log in, you are asked to log in through my access ID or some other thing, and then you get to this slightly easier to understand interface, at least for new users. One advantage is that then you don't need to set up SSH keys, but of course you have only those possibilities that are available through there, including login node shell. So this is exactly what I've done. And do remember that in Lumi, if you want to compile and run on the GPU activated nodes, you have to be in the GPU activated node or to submit a job that compiles that for you. So not on the login nodes. So take attention to the node name in front of the prompt. So this is user, this is node, and node is one of the GPU nodes. By querying SLRQ for me, I can see that. So I'm having an allocation. It takes an hour. Half an hour has passed. Half an hour is still remaining, and I'm logged into one of the compute nodes. I can also check that by asking what hardware is there, GPU hardware, by rockm SMI. And you can see, depending on the partition, I may inadvertently used standard G, so that has GPUs with 8 GPUs per node. Small g has, I think, 1 GPU per node. Otherwise, everything is equivalent. And one issue with the examples, code examples that you have currently on the Git repository or on the web page is that they are computationally inexpensive. So you run them, and it is nice. For example, with OpenACC and Fortran, it's nice that you can then query additional debug level and see what happens. when the programs run. With OpenMP, in general, you don't have that kind of debug information, at least not at first. So then the question from the end user point of view is, does GPU actually make my code run faster or not? But to be able to assess that, I need time counting, and I need probably a slightly larger problem to that. So for that, I will show you a slight modification of the vector sum file from the web page. And also I have put it there. I'm not sure if it's readable. So if you want to copy and compile and try and use it, you might check Scratch directory on the project. Let's see. Data sum.c file. So let me know if you are able to read this. I think it is readable. The file itself looks like this. Actually, I have three data sum, GPU sum, and OMP sum, but they only differ by one line. So by that OpenMP directive. Let me know if I should enlarge the font, but hopefully it is fine to be read. The directives that correspond to different modes of parallelization, including GPU parallelization, are these three. So lines 15, 16, and 17, 16, 17, and 18. The last one is OMP CPU parallelization, so PragmaMP parallel 4. The next one is GPU offloading with all default parameters. So it constructs targets, teams, and distributes the for loop iterations on those teams, and also tries to use in addition to that SIMD vectorization. And the topmost line is the one provided as a solution to the data mapping exercises, where you can also explicitly tell which arrays from your CPU memory should map to be copied and used in your GPU memory. And also for the code to actually take some more time, I increased the size of the array. Technically, well, I could do that by dynamically allocating memory on the heap, but as a compute node allows me to do things like that, so to take up almost 1 GB of memory on stack, I'm doing this. And lines 19 through 24 are slightly different. So you can see, in addition to the vector sum, which is by itself quite fast, even if your vector is 1 GB long, I'm doing additional operations that should account for more either CPU cycles or GPU cycles. And also some information at the end to tell me how much time the program has spent. So I'm closing this, coming back to the folder where now I could compile that code or versions of that code into programs that use different level of parallelization. First one would be not to use any parallelization at all, because, as was mentioned previously, OpenMP's directive-based model, if you ignore the directives, then it should perform as a serial code. So let's try to do so using CC compiler. Some little optimizations. I intentionally miss the -f OpenMP flag, so I will not even be using OpenMP. Then it's -o. And let's take that data sum file. I check that the executable got updated. So now it's CPU sum. And I will run it. I will run it, and I think I will have to speak now for around 20 seconds, because this is how it takes to perform that particular amount of computations on the single core of a Lumi node CPU. Around 18 seconds. Okay, so what happens if I use CPU parallelization by OpenMP? So the only difference will be me adding -f OpenMP and me using a source file where the correct directive is commented out or left uncommented. So that would be on some. Those files are otherwise identical. They differ just by the directive. Okay. And as you see, so now the code is parallelized over CPUs. It still takes almost the same amount of CPU time, because this is cumulative time of all the cores that were used. But as you saw from the time that actually took from me launching the program and it ending, now there are a lot of threads, I think 64 threads or something like that, on that particular CPU, on Lumi node. So time to solution is actually less. Okay. What would be the difference if I now use GPU offloading over OpenMP? Okay, so first I get a couple of warnings around loops not being vectorized. This is most likely the consequence of there being both directives to offload code to the GPUs and vectorize via SYMD. So in that case, compiler chooses to make the code for GPUs, but then it cannot vectorize that for CPUs, and you get a warning. I can run that, and as you can see, now the time is different because this is the time spent by a single CPU thread, while the calculation now is being done on the GPU. If I would have a second terminal to show, for example, ROCm SMI during this computation, you will see the node lighting up, one of the GPU nodes lighting up. Also, the output of the sum lets me make sure that I didn't change the answer of the computation. And finally, what happens if I add data mapping clauses? I'm compiling the same file that I provided into an executable named data sum. I get the same two warnings from SYMD. And I get slightly better performance, but not that much better. And this is because in this case, the example is relatively straightforward. So the arrays are being copied at once, and then they are being used. In a program where you would want to copy the arrays one time, but use the directive of directive multiple times, explicit data mapping, so creating data, structured data sections, and then entering, exiting, and updating them would be more efficient. In this case, this was barely needed for the particular computation, so therefore I can compare that again. The performance gains are there, but they are minor for this example. Okay, so that was my take on the OpenMP directive-based parallelization on C. It should work almost equivalently in Fortran.
Yes, I think we have time, and I would hope that you all can play the code on Lumi and following the instructions right here, and let me know if you miss something during the handout accesses. We can have the accesses until 2:20. Then we can have a 10 minutes coffee break.
Okay, thanks. So, so we just saw a few minutes ago that how one way to use GPUs to offload work. So this directive-based programming, it's quite easy, and you can take existing CPU code and then just add these directives and then slowly change from CPU to GPU. And also, depending on the compiler support, we see that this is also portable. Though there are some limitations, and it was also mentioned during the previous episode that OpenMP and OpenACC are standards, so they don't guarantee performance. They don't guarantee that if you have the same code on different compiler, the behavior will be the same, so you'll get the same results. But performance is not something that it's guaranteed by it. And also, there is some lag between these open standards. When you have new feature in GPUs, then it takes some time to get included in the open standards, in the OpenMP and OpenACC standards. And then, of course, you are going to have some lag to actually have compilers which start to support these new features. So if performance is critical, so if OpenMP is not enough, and you need some features that are not available, then of course the way to go is to start programming the GPUs, like I'm going to say, directly. So all free GPU providers, NVIDIA, AMD, and Intel, they give us the possibility to actually program this directly. So we can write the C code, and we explicitly express the parallelism, and we have to take care of everything. And first episode is about CUDA and heap together, and because you can say that this is something that only works for NVIDIA and for AMD GPUs. There is some portability between NVIDIA and AMD if you have heap code, but it's limited. While the tomorrow episode is about SYCL, which is also something that is portable. But if the compiler supports, then you can program also other devices and also CPUs with the same code. You can target also CPUs with the same code. So CUDA and heap are like direct programming, but they're non-portable. And the reason that they are together is that they are quite similar. So actually 90, I would say 90, maybe 95% of the features from NVIDIA have one-to-one correspondence in AMD. And so there are lots of applications where you can write an NVIDIA code, and then you can write in such a way that you can just do a simple search and replace, and then you go and write on the AMD GPU, and it will run correctly and with not much difference in the performance. So we saw before that when you program the GPU, we have so we can say that this is the programs that are running on GPU are CPU centric. So also you saw in OpenMP that practically everything runs on the CPU. So we have some device initialization, then we have some memory. We have some CPU GPU transfers to put the input of the data to the GPU. And then now what's different here in the CUDA heap programming model is that now we explicitly launched the kernel, which is the code that is going to be executed in parallel by the many threads. Well, in OpenMP, this is done under the hood automatically it's decided by the runtime how it's done. And we see that we have to write explicitly the code, so we don't have any more loops, as mentioned before. In the programming model, in the GPU execution model, we mentioned there are no more loops, so now we have to write ourselves the kernels. In the OpenMP, it was a little bit simpler, so we just put there and says, okay, I have a loop here, just split this loop over the threads and execute it in parallel. Now we have to specify exactly in the kernel what is the work that each kernel is going to do and how we want to launch this kernel so that it solves our problem in an efficient way. And the best way to look at this heap and CUDA feature is to actually just look over the codes and analyze the codes and see what happens there. So all CUDA and heap codes, they need these headers. So we have a CUDA runtime for CUDA codes, and we have heap runtime for heap. And we see that the code that we use for programming is actually just C, pure C. And then on top of this, we see that we have some extra functions. And here it's just to manage the device. So we have this heap get device count, which tells us how many GPUs this program sees in the system. So if you will be on Rumi and you allocate, you submit a job and you allocate some GPUs, now this will tell you how many GPUs this program can choose from. And then it's very important when running a GPU code that you use this heap get device. This way you can check that actually each program, or if you have an MPI code, for example, that each MPI code has its own device, and it's not happening that everything runs on only one GPU. So it's that this way is the first check to know that we are actually distributing our programs and our work over all GPUs which are available in the system. So in this code, we are not setting the device, but we just inquire the runtime on which device is my program running. So, and because we didn't specify anything, like we didn't set the device, of course, this will always be 0. But of course, we can also there is also a function that you can edit later in the exercise. Before heap get device, you can put an extra line, heap set device, and then you give a number. So if you have only one GPU, you'll put heap set device to 0. But if you have more than one GPU in the system, then you can put any number between 0 and the number of GPUs minus 1. If you have, for example, an MPI code, then you would somehow try to match that each MPI rank uses a specific GPU, so that each of them has its own separate GPU. There's no contention there. But this GPU is like the hello world, and we see that we set the device, so the device initialize the device, but all it does is tells us how is our code on what, how is our program run, what's the environment, what's the hardware where it's running. So if we actually want to do real work on the GPU, let's say this vector addition example, which we had it also in the OpenMP and OpenACC exercises. What we want to do is that what we want to do here is that we have three arrays, A, B, and C. So we have input A and B, and then we want to save the result into C. So there is no loop here when you run the GPU. We have this function, vector add, which takes as input these pointers A, B, and C, and the size of the problem, which is n, and then it extracts the global ID of the thread, TID here, and then it performs one operation. So the result C corresponding to this index TID is just input A of TID plus B of TID. What's different here for this function, we see that we gave this global attribute. So in by giving this global attribute, we indicate to the program, to the compiler, that this is a GPU function that is going to be launched from the CPU, and is going to be launched with some amount of threads. And here in the code, we can see one example of launching. So we have the name of the function over in the left side. In the right side, we see you have all the arguments, the input A and B and the output C, and the size of the problem. And in heap, both we have two ways to launch this kernel. So we can use this is CUDA style, and it's in a way easier, more familiar if you already had CUDA, to use this chevron. And then you have this heap launch kernel GGL, which has the same effect. It will create lots of threads which are all running this vector add kernel. But here in between, we see these variables, blocks, and threads. So these are two special structures. They are integers, and this instructs the GPU how will this kernel be launched. So this the second variable from the left, threads, this specify that how many threads we want in a block, and we see that here above we have defined that is 256, and blocks, it's the number of blocks that we want to be created, and in this call, in this launch, we keep the number of blocks as a function of the size of the problem, so that we launch at least n threads in total. So the number of blocks, which is given by this kind of formula, so it's n divided by 256 times 256, it's going to be at least n in this way. Now, when the kernel is launched and starts to execute on the GPU, of course, we have these arguments here, and this is memory that has to be available to the threads. And the threads only have access to the GPU memory. So these pointers that are here, A and B and C, they have to point to memory, which is on the GPU. When I started to do GPU programming, there was only one way to handle the GPU memory. So it's called explicit way. So that means that in order to have some pointers on the GPU, you would first you would have to allocate this memory by using this kind of calls, like you have heap malloc. So you give as argument the pointer, and then you give the size of the problem in bytes. And we see that we have two sets of pointers. So here we have AD, BD, and CD. And then also at the beginning of the code, we have this another set of pointers, AH, BH, and CH. And the reason for this is that we have two sets of memories. One is on the GPU that we need for working, for processing all the data on the GPU, and then we have this CPU memory. So if we start our problem by initializing the data on the CPU, like for example using this kind of loops, so we fill up our array A and B using this kind of loop, then later we need to transfer this data to the GPU. So after we allocated the memory by using heap malloc, when we also have two calls, heap memcopy, which would copy the data from this CPU memory, which is designated by this pointer AH to the AD, which is on GPU. So, and again, you have to specifically give the size of the data that is going to be transferred in bytes. So this should be capital N, not small n. And here, and an extra parameter to this call, we give the direction of the moving of the data. So in this case, because we are copying from CPU to GPU, then you have to put memcopy host to device. When you have the results finished, so the data has been processed, and now CPU cannot see what happened on the GPU. So we have to in some way copy the data back to CPU. And so here we see after we call this kernel, we have another call called memcopy, where we ask the GPU to send the data to us. And you see this again, the same arguments we have to give the destination, which is now on the CPU, CH, the sender, which is CD, the direction of the sending, so we see that it's from device to host, and then the size of the data in bytes. So one important aspect here when you run a GPU code and we do launching, so here, before the memcopy, we see there is no call, but when the code executes these instructions, so it launches the kernel, the control comes back to a CPU. So here, if you would have something like, for example, read something from the disk or write something from the disk, the program will proceed directly from this launch to whatever would follow here. But now when it hits this line, this is called a blocking. So this is a blocking call. It's a blocking instruction. And now, even if we don't instruct the program here to wait that this is finished, when the program reaches this point, it will just have to wait that both the kernel launch has completed, and then so all the data is processed, and then also the data that came back to the CPU. So this was kind of the older way to manage the memory. And there's an alternative to this, which makes the writing the codes a little bit easier. And most of the cases, there's no penalty in the performance. So now, in this case, first we have the same kernel, we have the same global function. We see that the calling, the launching of the kernel is the same. So we define the configuration, how it's going to be launched via these threads and via these blocks variables, and we do exactly the same call as we did before. But now in this version, when we use the so-called unified memory, we have only one set of these pointers, only one set of data. And we allocate this, instead of using the system malloc function or the GPU simple heap malloc. We use this so-called heap malloc managed, where to allocate this. And the same argument is here, the size of the size of array, of course. And when you use this kind of calls, as the name suggests, we let the runtime to manage where should our data reside. So it's not necessary to do all, it's the same, but in this version, we initialize the data using CPU. So here, we know it's on the CPU, this is a normal for loop. And so then when this happens, now the data is going to be residing on the CPU. Now the data has been initialized, and now when this is finished, now we go here. We want to do some processing of this data, and now we call this. We do this call. We do this launching of our kernel. Now, when this happens, the data transfer is triggered automatically. We don't have to do anything about it. So now, because the data is supposed to be processed on the GPU, then it's going to be moved. So now the pointer is going to somehow change the value, and all the data is going to be migrated to the GPU. And for the time when the data is used on the GPU, practically the GPU owns this data. So we have only one copy of the data at a time. Now, if we want to check the results from this addition, again, then we can just use, for example, a CPU call. So we do printf. But now, because the data is on the GPU, of course, there's going to be another trace transfer, another migration. The data from the GPU has to go back to the CPU. We notice here that we added this instruction, heap device synchronize. As I said, when we launch this vector add, if we wouldn't have this heap device synchronize, the code will proceed directly from the launching of the kernel to this print. So, and if the processing of the data is not finished, then when it reaches this point, it will trigger a copy of the data, and then the results will not be correct. So if you put the heap device synchronize here, we ensure that before the migration of the data, before we start to use this data on the CPU back again, we make sure that this kernel execution was completed. So these are very basic about how to run a very simple heap or CUDA code. So before going to the next part where we can see some optimization, if you have some questions, I think this is a good point to stop and try to answer.
Yes, let's see the questions and yeah, please leave your questions at the Hatem document and we can take later.
Yeah. If you get to this point, now we can use CUDA. Of course, it's not going to be the fastest code, but now you can actually get your hands dirty and you write whatever code. But of course, there is some basic optimization that you have to know about it, and then it will get you higher performance. So I would say it's not so difficult compared to the OpenMP.
Maybe a difficult thing is how to write the kernels. If you can consider that the kernel is just a function in the programming language like C or Fortran, it's the same. Just to handle how to call this, just launch this function from the main main part.
The first question is if this is the correct way to launch it. So no, so we are free. So there are 3 chevrons for launching this. I think this is correct, so as it is here on the slide. My brain now is a little bit smashed. Oh, okay, I see now. The second, on this slide, yeah, so on this slide there is a typo, sorry about this, since we use unified memory. So here in this launching, it should be A, H, B, H, and CH. Good catch, thanks. So, yeah, so it's when we, yeah. So when is the array transferred in unified memory? So when the code hits this line here, so it needs to use it, and this in launch is the first, the kernel, then it will see, oh, I want to access this data, A and B and C, but this data is not on the GPU. So internally, it will kind of trigger a mistake, an error, and this will trigger the migration. So that's my understanding of how this goes under the hood. But yeah, so it's only at the time when you start to launch this kernel. And just to comment here, if you have a simple program using the unified memory or doing the explicit management of the data of the memory, it will not it will have the same performance. But in other problems, you will need to explicitly control where the data is. Just when you have lots of CPU, GPU transfers, sometimes it is more efficient to actually do the copying by hand or give some hints to the runtime. Start now preloading some data from the CPU because soon we are going to use them on the GPU. So there's a new question on the hackmd. Why we subtract 1 when defining the block dimension? I mean, all C is like this. I don't know why. We always start counting from 0. So, like.
Sorry, I have a question.
Yes.
So with this unified memory, then how does it work with the? So if I want to just keep working on the GPU, then how do I enforce that? Like, is it just via the kernel? So if I keep calling kernels, then it will keep staying on the GPU. That's it. So it will not move back to the host.
Yes, exactly. So that's the easiest case. For example, if you have like a iteration, like Jacobi iterations, that you just want to do the same thing on the GPU many times, then like the fact that you are calling it all the time, you're launching some kernel all the time, then it will be it will stay on the GPU. So it's quite neat.
Okay, so it gets copied only once and then it stays there. Okay.
Yes.
Thanks.
So these blocks here, this formula, it's n plus 256 minus 1 divided by 256. Now there is a reply on the hackmd, so sorry, I now understand the question. So if we do it like this, that means that if n is not divisible by 256, then it will round higher up, and it will create like one block that is not complete. But if n is exactly divisible by 256, then having just n plus 256, it will give me one block extra. Well, this is not a big problem, but then I don't want to have just one block hanging around and doing nothing. We want to do it as correct as possible. Okay, so now let's see, I think let's move to the next part. So of course, this episode is not enough to go through all the features of GPUs. If you look at the CUDA programming guide, it has probably like between 300 and 500 pages, and then it changes every 2 or 3 years when we get a new generation. You have new things added. So, but there are some things, basic things that you always need to. You are always going to have to take care of them. And one of the optimization that is, in a way, let's say, easy to control as a programmer and can have a huge impact of the performance is this memory optimization. And we have two memory optimizations. One of them is like how to optimize when you have to transfer CPU to GPU, and how can you, in the kernel, how can you access the data in a way that we achieve maximum performance. So the first part is related to this. How do we access in a kernel the memory? And we have to go back to the hardware and to the way how threads are running on the GPU. So we see that we have cores, the CUDA cores are grouped in these units, and these units, they all execute at the time the same instruction. And we have these threads which are locked, and they all go to the same unit, and then they execute the same instruction. In addition to this, the memory requests, the memory accesses are done by per warp. So that means that if thread 0 needs some data, it's not going to get just one number, but it's going to get one block, which has 32 bytes or 64 bytes, so it's going to get several numbers. And ideally, we want that the other threads in this warp also need data from the memory, which are in the same block. And this is called coalesced access. The simple case that we saw here, the Victor addition, it's actually coalesced. So, and it makes sense, kind of that it's a very simple access. What would be a non-coalesced access? For example, here in this kernel, I multiply the index of the thread by some stride. So now, if stride is 2, that means that I only access every second element of the array. So now I will need, if I have a warp that requires 32 numbers, now the first thread of this warp, it will load 32 numbers, but 16 of these numbers are useless because we have this stride here. So we have to have two loads from the memory. If the stride is free, then we're losing like 2/3 of the data is practically not interesting for the warp. And if you have, if you can go higher and higher, so the highest you can get is 32, then you get the worst strided access. Another aspect of this memory access is the so-called alignment. So this actually has a much smaller effect on the performance. So if we see here that we added some shift, and the idea here is, for example, let's say the TID is 0, then when it requires data from the memory, if let's assume that shift is 1, then it will ask, okay, element 1 to be brought from the memory to the chip. But the way memory loads works is that it will load from 0. So we are kind of losing one element is just loaded there and is not used. And now if the thread is 32, if TID is 32, then you can say that the element 32 would be useful for the other warp, but is not useful for this work. So if we have the bigger shift it is, the performance starts to decrease, but then again, it's when shift is, for example, 8, and we go back. But now NVIDIA and also AMD, they kind of solve this problem. So actually the penalty performance from having this kind of not aligned accesses, it's actually very, very small. And so we have lots of very good cache. And also even for the stride accesses, now maybe it's not really the worst thing that can happen, but still, if you have a program that is bandwidth limited, then we want to actually do some extra work to ensure that the accesses are coalesced. There is one simple way as a programmer to figure out if the access is coalesced or not. So if we take this TID, if you take this thread that has the index TID, now the next thread in the warp, let's say it's thread IDX plus 1. So now here we see that if we have two threads and they're separated by one thread will access TID and the other one will access TID plus 1. These are close to each other in the memory. So this is a very good memory access pattern, because when it loads the block of data from the memory, they are near each other, so it doesn't need extra. Now, if we go here, when we have a stride, let's say the stride is 7. Now, if we have two threads near each other, then we have 3IDX. This TID changes. This access here changes because if we put thread IDX plus 1, then we have here TID plus stride. So now, maybe for these two elements, we are in the same block, but then the warp has 32 threads. So if you have a stride of 7, then one block will serve only 4 threads. And now we have lots of other threads that require, again, loading from the memory. So that's maybe it's one way to figure out. If the access is not clear, if you don't know if it's coalesced or not, then there are also some tools that can help us determine how efficient is our memory, how efficient is our pattern. And there is a way to fix this by hand, and it's by using this small on-chip memory, which is called share memory in CUDA and local share memory in heap. So the threads which are assigned to this specific SMP that are part of this block, they can actually write to this memory, and also they can read to this memory. So in practice, you can have these threads bring a chunk of data in the coalesced way, and then after that, in the kernel, once the data is on the share memory, they can all start to access this in any kind of random way. The penalty for doing that is very small. So you can somehow fix bad access patterns. And one example where shared memory is critical for performance, it's for example, this matrix operation, like for example, transposing. So if we have initial problem, a matrix like this, A, now after the transposing operation, this layout is going to be like this. And if we look at this case, we'll see that actually there's no computation, but so it's only memory transfer. So we can see that the bandwidth, if we do it in the naive way, it's quite small. And so we can also learn something about more about the heap kernel language. So we can look at the transposing and the optimized way, but before going that, let's start do it in a more, I'll say, go slowly there. So first, okay, so you have the GPU and it has some theoretical peak. If you have the V100 cards, and this is 900 gigabytes. The newer cards have a much higher bandwidth. And since this is just a memory operation, we can just take our base to compare how good our code is, just do a simple copy. So we can compute the bandwidth that our kernel here, which is called copy kernel, achieves when you just take the data from one memory location, put it in the other one. So in this case, we see we have here a two-dimensional grid. We have thread idx.x, we have thread idx.x.y. Also, the blocks have block idx.x and block idx.y. We see from these interesting variables, from these coordinates of the threads and blocks, we can construct this x index and y index. So this would correspond to I and j indices that were in the previous slide. And then, because in the GPU you don't have two-dimensional matrices, we flatten this. So the global index of these coordinates, x and y, it's just something like this. So it's x index plus the number of columns times the width, number of rows times the width of a row. And we just put the data from input to the output. When we call this kernel, we see that each block contains tiled-in times tiled-in threads. So if the tiled-in it's 8, then we have 8 times 8. If it's 32, we have 1024. And then we have this block x and block y, which is defined as the width divided by this and the height divided by this. So we are assuming here that the size of the problem, the width and the height, are divisible by the tiled-in. So this is a very simple copy, and now in a full code, we can compute the execution time and then divide by take the total size of the problem divided by the execution time, and then we can find out the bandwidth. So in this case, my calculation gave me 717. So I think that the size of the problem that I'm using here, which is 4096 for each dimension, is not big enough. So maybe that's why I'm not getting the full bandwidth. So this is our reference. So now we go, and let's say we are going to do the transposing. We use the same calling so that we have the x index and the y index. And now we read the data from the input at this index, in index. And now if we look at this in index and we say, how are the memory access here? What happens if two threads are near each other, have indices close to each other? So we put thread idx plus 1 and see how does the E index changes. We see that if we put thread idx plus 1, it will change with x index plus 1. So practically, in index only changes plus 1. So the reading of this here, it's actually done in qualist way. That's great. We don't have to do anything. But now, if you look at the out index and look at the formula, how it's here computed. So here, x index is multiplied by the height. So if we change the thread idx and we add 1, now we see that the out index jumps by height. And now practically every write to the output of this kernel will have to trigger one block transfer from the memory to the GPU cores. And of course, now if you look at the effective bandwidth, it's just a little bit half of what we got from the copy. But then the question is, can we do better? And of course, yes, we can do better. And we want always to utilize all the resources of the GPU. So, even if it's not so bad result. So this is where the shared memory comes into play. And in order to use the shared memory that is present on a streaming multiprocessor, we define an array. We call it tile. because we take a small part of the matrix and we give it this attribute shared. So now the GPU knows that this array, where does it reside, and so now the GPU knows where this GPU is going to reside. And now the transposing is done in 2 steps. First, we fill up the data into the shared memory, and then from the shared memory, we write the data into the output. And now if you look at this in index, the formula is a little bit different here, but if we check here with thread IDX, we see that if we have 2 threads near each other that have thread IDX just by 1, the index only goes up by 1. So the reading from the input and saving to this line where we save into the shared memory is actually done in equalist way. Now, from this memory, now we have to save the data to the output. Now this is the so we use this out index, and we see that the out index again, it is defined also in a way that if thread IDX is +1, it only goes +1. So now we see that we read in a equalist way, we save to shared memory, and now we write back to the output into the equalist way. There is some games here with these indices, the way it's computed, and I'm not sure how to explain it properly. This requires a little bit of working and thinking about making some drawings. But just have to believe that these indices work, and the result of this is that now the effective bandwidth of the is transpose is 674. And I think that's quite good job, because we haven't made the code so much complicated here. It's not much longer. It's just few lines extra. So just some other comments about this code. We see here that here we save the data into a shared memory, and here we have async threads. So the reason for this is that we want to be sure that the data that some threads are putting into this array has already reached this shared memory, so that here when the data has to be read to write it into this by using this line, it's there. Otherwise, there's no guarantee that the data is there. So by putting sync threads, we instruct that the kernel execution pauses, and all threads, they come until here and here. They have to wait and have to be sure that all the other threads have done their work. Now, so there is a limited synchronization of threads, and only can be done inside the block. So now we got this bandwidth 674. So of course, maybe there's some other optimization and tuning that can be done here. There's one actually in particular that is important, and this is related to the way the shared memory is constructed. We can think of the shared memory that it's a set of shelves. So when we start to load this data from the global memory, we start to put, each thread puts one data in each of its shelves, and then it fills up this array. But then when you get back here and we have to read the data, we see that the data is read in a transposed way. So now all the threads practically want to read from the same shelf. But if many people, for example, try to go and grab something from the same shelf, you end up in trouble. So you have contention. So this can affect the performance. And the solution for this is actually, in this case, simple. You make the shared memory one dimension +1. And now the way the data is distributed over the shelves, it's in such a way that both the reading and both the writing here and also the reading here, it's done so that each thread access data that is in a different shelf in the GPU terminology, they are called banks, memory banks, and all GPUs have it. So now we got our bandwidth from 674 to 697. So I think it's not so big. It's less than 10%, less than 5%, I guess. But other problems, this can be more. We can have bigger effect. So again, as a user, as a programmer, we cannot know for sure what happens there. So we can use profilers, but in general, and that will give us a really good idea if we have conflicts and if there's some way to fix them. In this case, because we know how the GPU is constructed and we know this size of the tile dim that we can put in, then we kind of can predict how is the data going to be distributed in these memory banks and how it's going to be even read. So we can use this to improve the code. So this kind of memory, we see that it improved our kernel execution by a factor of 2. In share memory can be used to improve the memory access also for other stuff. So for example, if you have an n-body problem, you can have, like, for example, load parts of the data into the share memory and then start to do n-body problem of this data that is inside on the block, and you can avoid actually loading the data n times. So this is quite an achievement, I think. So another example, another type of problems where share memory is actually critical, and actually I think it will be very difficult to actually do this without share memory, are the reductions. So these are operations where we have an array and then we aggregate this array to one value, and by doing some binary operation. So for example, if we want to know the sum of an array, that's reduction, or if you want to find the maximum on an array or the minimum, it's again another type of reduction. You can also have like logical operations, so not just math. And in order to be able to do reduction in parallel, there are two assumptions. Now you have the commutativity, so if you have a plus b equal b plus a, of course this can be any kind of binary operation. Of course, in our case, we only use commutative operation. The next one is also important. So in order to be able to do things in parallel, this means that the order of operation that we are doing on an array, it will be changed. So we need to have this kind of associativity. So it should give us the same result if we first do a plus b and then we add c, or if you do first b plus c and then we add a. So I think all the example that we see here on the slide is actually this happens. So up to the numerical, up to the machine precision, these conditions are fulfilled. So then we can do this in parallel. The main idea when you do reduction in parallel that you divide the problem subsets and then you try to process these subsets in some way. And on the GPUs, the natural way to divide this is that we give one subset to one of these streaming multiprocessors. So then we divide our problem in blocks, and on each block we process one of these parts by itself. And then at the end, we of course have to get back the result somehow. And now, if we have one subset of the problem and we just put it to be processed on a block of threads, here again we want to take advantage of the parallelism inside the block as much as we can. So we cannot just make a loop and say, okay, now go over each element and see what happens, because GPU don't work like that. They want to do many things at the same time. So there is a very efficient reduction algorithm which works at the block level and looks like a binary tree. So let's assume that we have a big array, and now our block here has four threads, and we are loading from the memory 8 elements. So now what we do here is that we take these 4 threads, each of them takes one value from the first half, and then you add a value from the second half of the data that is local to them. Now we do this, now we have reduced our subset to half, and now we can do the same thing again, but now you only need to use two threads. So again, each of these threads will add 2 numbers, one from the first half and second from the second half. Then now we get 2 numbers, and now 1 thread, it will give us the result. Of course, the last part of this is not the most efficient, but at least up to some point, we have quite good efficiency. We have warps that, as long as 32 threads work, then this goes this is quite efficient. 32 threads, sorry. And the code for this kind of problem, it can be done. So it's just one page, this one slide. And let's assume that we have a array X, which is double precision. And then we are going to save the results for each block to an array called sum. And the size of a problem, of course, it's n. So here we define the shared memory, and we make it 2 times this TPB. So our block will have TPB threads per block, and we initialized this to 0. If we do other operation, we have to do different initialization, and then each thread we ask it to load 2 elements. So first, it will load an element which is has the index smaller than n divided by 2. Sorry. And then the second one, it will load another element which is bigger than n divided by 2. Here, then we wait for the data to reach the shared memory, and then we start this binary tree reduction that we saw before. We start with the first loop will have all threads working. In the first iteration of this loop, all threads will be working. So it will do one addition. Then, because the problem now halved, we are going to have half of the threads which are doing the same, but now we have again half of the problem and so on until we are left with only one number. Now at the end, when every iteration we see that we have to synchronize the threads because we are still working with shared memory. So we have to be sure that data that is accessed in the shared memory by one thread the data is there. So that if the one thread accesses some shared memory that later is going to be accessed for another one, we have to be sure that data is there. So at the end of these iterations, when we have only one number, then we can decide what to do with it. So one option is to save this number into the GPU memory. So we have a new array which contains all these partial results. And if this array is very large, then we do again the same kernel. We can call again the same kernel. Or if it's not large, then we can do something like this kind of this atomic operation. So this atomic operation, it's adding my number to another number. There is a typo here. But when it's accessing the memory, it ensures that no other thread will access that memory location. So it avoids using atomic add. it avoids race conditions. Of course, because when you do this, all accesses are serialized. You should, in the code, this should be used as least as possible. But if there are not many, then we are not going to see a big performance penalty. Okay, so this is all about 2 examples about how to use shell memory and how to avoid using the global memory, and how to improve the pattern access using the shell memory. The second type of memory optimization is the how to overlap data transfers with computation. And like as I said, when you call a kernel, you can already do some operation on the CPU, but I want to do something different. So let's assume I have a big problem and I only have one thing to do, like in a vector addition. I take my data which is on the CPU, I transfer it to GPU, I do the processing, data parallelism, no summation, just every element edit, and then I copy the data back to the CPU. But now, when I initiate the copy from the CPU to the GPU, GPU has to wait for some amount of time until the data is there. Then, when the data is copied, when the results are there, now the data is ready, we want to transfer it back to CPU. Again, the GPU stays there, does nothing, and that's bad because you are practically losing millions of operations that could be done this time. So what we can do is that we can divide our problem in smaller parts, and then we can start to copy this data with small chunks, and then when they reach the GPU can start to work on them, and then in the same time we can also initiate other copies, so that in this way we would overlap some of this copying and computation. And CUDA heap, they have something called streams, where the book definition is that a stream is an independent execution unit which executes a sequence operation in the order there issues on the GPU. So in a way, it's very similar to a CPU thread, but it's not really a CPU thread. The one thing that we know there, which is important for us, that all the operations that are going in one stream are dependent on the other ones that are in the other stream. And let's see how we can use this for overlapping computation and memory transfer. So if we look at the way we did this first vector addition code, now we have 3 engines on the modern GPUs. So we have copy from host to device, we have the kernel engine that does the computation, and then we have the copy. This should be device to host. So, and all these 3 operations can be done at the same time. So these are three devices on the 3 chips on the GPU that can do things concurrently. So the original code that we did for vector addition, what we did, we copied the data. Now when the data is on the GPU, we reach this point. The data starts to be processed on the GPU. Now we reach this point, and now the data gets copied back to the CPU. So let's assume we split our data in 5 parts, 5 chunks. Now we take the first chunk, we initiate the copy. Now when this one gets to the GPU, now it starts to be executed. So we see it here in the timeline. But in the same time, now that the copying, the host to device copying engine is free, now we can actually initiate another copy. So at this moment, we have 2 operations overlapping. Now when the data from the first chunk is ready to be sent back to the CPU, we see here that it starts the copying from the device to the host. Now the second chunk is ready to be processed by the GPU, and then the third chunk now starts to be copied. So we move the time from left to right, and we see that things that are on top of each other are actually executing at the same time. And this is in a hypothetical case, but we see that here, for example, we reduce the total execution time by half. Of course, there is always some overhead to create the streams and to launch the streams, but in practice, we can see performance in many problems. And if we try to put this in the code, now it looks a little bit more complicated, but let's say the amount of code that is needed to implement this is not really so big. So if we take our vector addition code and we do the explicit memory handling, so we have a set of pointers which are on the CPU, a set of pointers on the GPU. So now instead of copying the whole data, we see that now here we have a loop. And in this loop, each is doing the same operation, but to the small chunk. So first is doing a memcopy async. So it's copying a chunk from the CPU, from the host array to the device array. But the size here is not n, but it's n divided by n streams. We have the array action, host to device, and then we see that we put an extra parameter here, the stream I. Same with the P array. And now we can launch our kernel, and we launch it with this pointer where our chunk of data starts. And then we launch this copying so that we can get our data back to the CPU. We see that when we do this manual explicit handling of the memory, we use this async versions. So that means that when this is called, it gets put in the stream, and then the CPU goes next. So it does this call, and it goes directly to this one. It doesn't wait for the memory transfer to happen. It just says, okay, I want the data copied. Again, I want the data to be copied. And now says, okay, now execute this kernel. And all these operations are now sent to the GPU, and they're going to get executed in the order they are sent. And so, and then at the end, okay, we have to do some extra work to synchronize this with the device and to get the final results. So for the vector addition, I know this would be maybe too much if you have never programmed before GPUs, but it's a good exercise to work on this and see what happens if you do it this way. So take home message from this session: when OpenMP is not enough, because it's not fast enough or because features are not available, we can use direct programming. And for NVIDIA and AMD, this is CUDA-C and HIP-C kernel languages. We put them together because they are actually quite close to each other. So 90 to 95% of the codes from CUDA can be mapped to HIP. So there is very close relationship. And we also saw an example of what kind of optimization we need to do on the GPUs. And I think that this kind of optimization is something that almost all applications need. The memory optimization in the kernel is something that any kind of problem that is not vector addition is needed. And then the overlapping data transfers and computation is needed in these kind of cases where there is like a distributed problem and there is communication with the other nodes. There is also like parts that are going in the CPU. The CPU maybe could be reading data from the disk and then feed up the GPU with some data. So we need to make sure that we overlap some operations and that the GPUs never stay idle, because I mean, I think the theoretical flops of a GPU is something like terabytes. So 1 second of staying idle is like 1 billion of operation that has been wasted, 1 billion of cycles. So we need to use everything all the time. avoid this. So for this problem, I suggest to go back to this material and go over it again, look in more detail to what has been presented now. Then there are some exercises in this content folder, example CUDA heap. There is some basic instruction how to run this. So for the exercises, my recommendation is to take all these examples that have been shown here on this page and then just try them. For the difference is that, for example, for the hello world, you can just try to launch, for example, one program with many GPUs, not just one program with one GPU. And you can try to run, even if you don't put MPI into your code, try to see what happens if you launch the same program, like with more than one tasks, for example. So you just run the same thing. And so just look over these codes and see, play around. But for the memory transpose example, I haven't tried it on Lumi, so I'm curious what are your findings on Lumi? How is this algorithm that was shown into this episode behaving? How close do we get using shared memory to this simple copy kernel? Yeah, thanks. That's all.